Okay, so can I just do a little intro to the website?
Yeah, go for it. It's yours.
My
I'll just scroll for you.
okay. All right. So this website is hosted by the New England Board of Higher Education. They very generously host this for us. They were actually our PI on the first 6 grants, NSF ATE grants, was from NEBI, and we get along with them very well. In any case, so there's a lot, as you can see at the top. It's a little tricky, but um, the usual stuff you expect. But the lower level there, photonics teaching resources. So I always like to point that out because that's my baby, and that's where we started. Maybe you could just go to resources for teaching optics photonics, which is like the middle one, I think. Yeah. So it's not artistic, but it includes a couple of books. In fact, if you do outreach, can I do a little self-promotion,
Yes, go
especially
for it.
being given away for free? We just had the second book down is called Exploring Light, Investigations for Optics Exploration. And these are actually, they were outreach activities. Many of them were shown to us by our participants. We started together in '95. So it's been 30 years of collecting these. And when I retired, I asked SPIE if they would consider publishing it. And they said, sure, and we'll make it free. The printed book isn't free because somebody has to pay for the printing, but the PDF is free. And it's just a collection of really cheap, inexpensive outreach activities that you can do. And it was a lot of fun putting it together, taking all the photos. There's also, we have our own YouTube channel. If you want to see what Nick and I look like in 2006. Uh, there we
Sorry.
are, uh, doing experiments, and there's photos and all kinds of. With a partner, I created an online. Again, all this is freely available. It's on this website. It's called Dumpster Optics, and it's teaching optics from stuff from the dumpster. I had a really nice lab at Three Rivers, but you can't really take that on the road with you. So we developed it with junk. A lot of toilet paper tubes and aluminum foil and that sort of thing. So anyway, that is one little corner of our website that I didn't want to be missed. All right, Nick, back to the
Yep.
challenges.
Okay.
So
So the ch
right
the
there. Yep.
challenges. Okay.
And now, speaking of, since you mentioned just science, if you scroll down, you notice that there's all kinds of I mean, we've had so much fun doing these, and we learned so much. We learned how to refurbish a cranberry bog. We learned how to laser strip very fine copper wire. We went up on the roof and saw some very unique solar panels. I mean, we've really there's so many different topics here because our challenges, our grants were, the first one was photonics, the second one was sustainable technologies, third one was manufacturing, and the fourth one was photonics manufacturing. So there's a whole bunch of different topics. And I found that with reluctant faculty, sometimes it's, if you say, well, what is for example, the first lab in physics, density of a cylinder, could anything be more boring? I mean, that's what they did at Three Rivers for decades. And I said, what are the goals of this? You want people to find out where the lab is. You want them to meet their lab partners. You want them to understand the measurement process of doing calculations with measurements. And you want, that it's very basic stuff, and you don't have to spend an hour with a vernier and a cylinder to do this. So we would do when we developed in Philadelphia, the Tacony Frankfurt Watershed Partnership, which was again on, it was an urban stormwater project. So it's and what happened, instead of the lab being totally silent, it was extremely active, and people were actually talking to each other and bonding. So there's a lot more that, what I'm saying is, there's a lot more you can get out of this than just teaching and learning this particular material. So this is the second one we did with Anu. The first one, actually, That I really love that because it's a math problem. It's a geometry problem. And fit a waveguide into a box subject to constraints. I can see doing it with yarn on a piece of paper. So you might want to look at that. And then the one we did here, Future IC, that is also new. So you want to click on that, Nick? Okay. And they all look the same. So do you want to talk about why we have these 5 sections?
Sure. So on this first page, this is the introduction. So it kind of tells you what the problem is about. In this challenge, you'll develop a measure to minimize wastewater from a CNP process and a semiconductor fab. Talks about some of the STEM principles reinforced, but all of the pages, each challenge that are in this list of challenges, they all have the same format. They all have 6 pieces to it. There's an introduction, which gives you an overview of the problem in general. So, why is this important? Then we have the organizational overview. It kind of gives a commercial for the either the company or the research lab. In this case, it was MIT that solved this particular problem. Then we have 3 pieces here: the problem, the discussion, and the organization solution. So the problem is a reenactment, an actual reenactment of the people who were involved in initially getting this problem and solving it. How is it presented to them? And one of the challenges of real world problems is, most problems that are real world are ill structured. There's not enough information to initially solve it. So you really have to come up with a strategy, which is what these are all about, a structured problem solving strategy for attacking problems. So the problem is reenacted. We used to use actual video, but it didn't work really well because people thought they were actors and stuff. So what we did was we did a bunch of voiceover stills. The audio was really awful. So we took a million pictures, and we created a script based on what was said because we recorded the conversation, and then we did voiceovers on the stills, which actually made it much easier to put these things together. So the
It also
problem,
made it, excuse me, I just want to say makes them easier to edit. So
yeah,
if we show it to the partner in company and they say, no, 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 I don't like that, we don't have to get them to sit for another video. We can just change and we've had to do that.
got a couple, yeah, that got updated, right? So the problem basically kicks the problem off, and embedded in the problem statement section, there are additional resources, what we call the problem solvers toolbox, that students can use to help guide them through the problem solving process. So the students are usually let free, in teams to go and try to create, come up with some kind of idea solutions. But at some point, they're going to hit the wall, like students always do. And so we provided the brainstorming discussion that the company or the organization actually had, that the discussion that they had or about the problem, to kind of give hints and guidance towards how, what were we thinking when we solved this problem. Kind of gives enough information so the students can come up with an actual solution. Then at the end of the day, students will come back together, whether if it's a week later, 4 weeks later, 6 weeks, depending on how you implement it. They come together and they do a presentation of their solution. And the important thing is they need, we require that they explain the thought process that they went through in solving their problem. They need to rationalize everything that they do, which is what the real world is all about. These 2 sections, the discussion and the organization solution, are password protected, so that if you're the instructor, you can let them beat their heads against the wall as long as you want, before you give them the password to access these 2 sections. But generally, after all the students have given their presentations on their solutions, all the team, we present the organization solutions. This is how MIT solved this problem, or this is how photo machining solved this problem, which creates an opportunity to compare and contrast solutions. So students, once they see how it was actually solved, a lot of students are very close to what the company or the organization came up with. So it kind of reinforces their self-efficacy for problem solving, which is nice. A lot of times students may actually come up with a better solution. We don't know. This was kind of a unique problem with working with the Future IC project, in that there really was no solution other than the way MIT, I take that back. There was not just one solution. The one that we did have was the one that MIT uses to recycle, reclaim their water. But there's a lot of opportunities for students to go out and brainstorm it, like think outside the box on this one. So it's kind of an exciting problem. Each section has its own additional resources, or in this case here, because it's the front page, this is the credits. But every section has its own additional resources. So I'll keep it at that. And if you
Can you just point out, because we'll come back to this, but so they know
yeah.
where it is, the teacher resources.
Oh, teacher resources, yeah. So teacher resources is here, like you said. We'll come back to this after. So if you watch this whole problem, you go, "Hey, that looks like something really cool. I like to do in my class." But I don't know that much about CMP. We provided all of the information on not only what CMP is, tutorials, assessment details, and tests and concept maps, and everything you need to implement this in your classroom. All the teacher tools.
Okay.
All right, ready for?
Before you
Yep.
show the video, I just want to say that, go ahead, you can click on it. The introduction video is the most fun for me because I can just kind of go wild and I do a video on sensors or the history of measurement or whatever. But I saw the Future IC video and I said, there's just no way that I can come up with something as gorgeous as this. So instead of me putting together
She's talking
something,
about you, Anu.
yeah, I know it's just
Thank you,
me.
thank you, thank you.
So
Appreciate it.
So what I did was to take an excerpt from it, because one of the things we've agreed on since the very beginning is that at least community college students tend to have very short attention spans, and we try to keep videos to 3 minutes. So go for it.
Ready? Here we go. Hopefully this plays.
Human existence is at a crossroads. The balance between humans and nature is being severely challenged, driven by a relentless appetite for consumption, none more so than in electronics. We throw away cell phones, computers, and appliances too frequently, creating mountains of electronic waste.
The size of the market in the next 10 years for microelectronics is going to be on the order of $1 trillion.
People, especially in the Western world, want faster internet, ChatGPT, and self-driving cars, which require electronic chips to be made smaller. And this comes at a huge environmental cost. The bottom line is that 4% of the population uses 24% of the planet's extracted resources. Every year, the world produces 50 million metric tons of electronic waste, while the microchip industry uses unreplaceable scarce minerals, over 200 terawatt hours of energy, and over 250 billion gallons of water. This is neither scalable nor sustainable and cannot continue.
Isn't that beautiful?
It's a beautiful thing. So
And
Beautiful problem that we have. Yeah.
Yeah.
so the resources include the entire video, a link to the entire video, and then there's a little article about what it means. What does refurbishment mean? And it's from a refurbishing company. So we try to have a few other things that you can point students to get a little more insight. Okay, now organization overview. One reason for doing this is at least, I don't know, I think things have improved, but when we started doing these, it was not uncommon for students. Well, first of all, they're first generation students, and they've never been in a workplace aside from maybe fast food, or around here it's the chicken farms. So we wanted them to see maybe not so much this organization overview, but for a company problem, for example, this is a place, there's real people that work here, and they tie their shoes and comb their hair, and, and they don't wear really torn t-shirts. And, we want them to see
they
that
carry notebooks.
they carry notebooks, yes. So this is an ad for the company and a little insight into what they do.
The Future IC Global Research Alliance for Sustainable Microchip Manufacturing, funded by the National Science Foundation's Convergence Accelerator Program, is an interdisciplinary team of scientists for both industry and academia, and led by Dr. Anuradha Agarwal, Principal Research Scientist at MIT's Materials Research Laboratory. Future IC conducts research aimed at solving especially compelling societal or scientific challenges to sustainability in electronics manufacturing, using a multidisciplinary approach to create high-performing materials and products that are sustainable. Future IC will drive economic development by reshoring semiconductor manufacturing, thus bolstering national security, economic sustainability, and supply chain efficiency. The Alliance will foster future innovators and enhance workforce training with sustainable semiconductor literacy in microchip technologies to recruit and retrain students from elementary grades through adults. Future IC will support leaders with varied backgrounds across the talent pipeline to ensure that research is informed by a broad range of perspectives to shape future technology trajectories. And it will create coherent technology evolution while considering the impacts of processes and designs on sustainable high-volume manufacturing.
So again, with this video, there's a separate resource section for the overview. Want me to show this, Judy?
Yes.
Okay. So we have, go ahead, Judy. Sorry.
I was going to say, we always have the script. Closed captioning has gotten better, but with the script, you can be printed out and you can, you get a better idea of what people are saying if listening's a problem. And then there are some other links to it's hard for me to see, but yeah, the Future IC video and some articles about it. Yeah. I just, I forgot to mention that the reason we do have to run these in Chrome is that, I don't know if you've run into this, but YouTube has a new policy for embedded videos. They don't want you to run them, even if it's your video in your website. And you have to go to YouTube to run it, which is very disruptive because it's much easier to run it right within the frame. And then you have to look at their recommendations for the next thing to watch. So if you run it in Chrome, it seems, at least for now, that you have a little bit more control over what's happening.
So the next part is the actual problem statement. So this is how a news team received the problem.
As you know, Justin, semiconductor manufacturing is very water intensive. It relies on water at all stages of the process.
The chemical mechanical planarization, or CMP process alone uses vast amounts of water. It amounts to about 40% of the industry's water consumption. A research fab like ours might use up to 30,000 gallons of water in a day, but a high-volume commercial fab can use millions of gallons of water every day. And the wastewater is dirty, acidic, with slurry particles mixed in.
Right. But CMP is an absolutely essential process in making chips. Look at this presentation I gave to some students last month to explain why we need to use it as part of the chip-making process. We usually start with a pure silicon substrate. And let's say the first step is to put down a silicon dioxide, or SiO2 layer. Next, we want to etch the SiO2 layer, and we're left with a non-planar surface. Suppose we want to put a nitride layer on top of this. You can see there's a bump or a kink. It's not flat. But the surface needs to be absolutely flat for the next photolithography step. So what we do instead is to put a thick layer of nitride, much more than we need. Then we use CMP to polish it down so it's flat. We have to do CMP every step so that we get a nice planar surface for the next photolithography layer.
It's a pretty complicated process, and it uses ultra-pure water from beginning to end. The question is, what can we do with all that wastewater when we're finished with it?
Therein lies the question.
And that's
So,
when, what? What do
go
you
ahead.
want? They look like, as Nick always says, deer in the headlights.
Yeah,
What do
yeah.
you want me to do?
Yeah.
So this is where the problem-solving toolbox comes in. So
Yeah. So if I
you
click
should be
on,
able to pull up a PDF now, Nick. If you,
say again.
okay, click on it. And I added under problem-solving toolbox, if you want to pull up the actual whiteboards, there's a PDF there.
Okay. Right here.
No, up higher.
Oh, sorry. PDF.
Right there. Yeah. Okay.
Got it. Sorry, my eyes are going. Sorry.
I know it's really, really small.
So you want to explain these?
You can.
Okay. So the
Really,
whiteboards, the whiteboards we've been working on since 2006. And initially they were inspired by House MD. Remember House, the TV show? But whenever they had a problem, they would all gather in front of the whiteboard and throw down their ideas. And so we came up with a process that has 4 steps to it. It's basically the engineering problem solving cycle or the scientific method, but kind of condensed down into form. So we have the first step in problem solving is problem analysis. It turns out one of the hardest things about problem solving is actually framing the problem, defining what it actually is. So the students will get these PDF forms, and they can write them up on a whiteboard, they can take them home, they can do it on a computer, whatever. But the idea is to clearly define the problem. In this case, what do we do with all this wastewater? So, and this kind of walks them through what's the criteria for a successful solution. So they start listing criteria. What do we know about the problem? What specifically do we need to learn about the problem? And then are there any assumptions? Because there may be some missing information, so sometimes you have to make assumptions. Once they've gone through this first cycle of the problem analysis phase, they jump to the next one, which is independent research. And this is really a backdoor way of teaching self-regulated learning. So as a team, divide up the learning. Who will do what? How much time do we have to complete the research? What is our plan for acquiring the knowledge? Where are we going to get the information? So they divide up the learning, and then they go off into their happy studenthood, do their research. And this could take a week, could take 2 weeks, could take 3 days, however long you want to give them. And then they come back and they do a brainstorming session. Brainstorming is an interesting, it's really, this comes from some of the, some industry-based ways of doing things, but listing out your solution. So they present their solution ideas. They go through a list of pros and cons of each idea, and then they rank them based on, what they as a group think are the most appropriate ways of moving forward. And then once they do that, we make them go back and list the original criteria. So here's what you said the solution had to address. And then step by step, item by item, how does your solution address each of the criteria? And then if you were to validate your solution, how would you do it? How would you create a test plan for this? How could you do that? So it walks students through this problem solving cycle. If they don't come up with a viable solution, then it starts all over. They go back to the first one. It's a recursive process. So let's see, where am I? Back. Yeah. Okay. Good. Okay. So that's the problem solver's toolbox, and I'm going to go back to here. So we're still at the problem statement. There are additional resources here also. So the additional resources for the problem statement, again, we have the script. We have an article on, water's crucial role in semiconductor manufacturing. And then, Judy, you want to describe this video here?
Yeah, while we were in the fab, Justin gave a demonstration of the CMP process, and we had made a video of it, so I edited that into, I don't know, it's a few minutes of exactly what do we mean. You saw kind of a picture, but a diagram, but here's what it actually looks like.
Yeah. So I'm not going to go through that right now, but let's go to the discussion. So your students have gone through the first round of filling out whiteboards and working as a team to try and come up with a solution. But then they hit a brick wall, and so we give them a password, which is, this one is PD.
Uppercase P. Can we tell them the secret?
Yeah. 2139. You can tell them
Yeah,
the strategy.
they're based on zip codes. And that was mostly help us remember them.
Yeah. So this is the discussion video. So let me show this.
So Justin, where do we get DI water? Do we have to buy it?
No. We make our own deionized water, which is also called ultra-pure water. The first step is a mechanical filter to remove larger particulates. Then it will undergo reverse osmosis, or RO, ultraviolet exposure to remove bacteria and deoxygenation. It's stored in a tank that continuously recirculates through the last steps. In this process, up to 40% is diverted to waste to maintain the correct pressure for RO. If the pressure is too high, it will force more particulates through the membrane. We clean this wastewater to gray water before it goes down the drain.
So do we put DI water in a special kind of storage tank?
The tanks and feed lines are made of materials that don't react with chemicals. And while the tank has continuous recirculation, so do the feed lines. There will be a return back to the tank at each point of use, like a faucet.
And how much DI water do we use each day?
I'd say 30,000 gallons per day or more, but a big fab like Intel would use something like 13 billion gallons per year, and there are about 20 fabs in the world at that scale.
So the real problem is the dirty water from the CMP process. Is there a way to clean it enough for reuse or recycle?
So that kind of is a leading question to get students to start thinking about, okay, how do we clean the dirty water, the gray water? And is there something else can we reuse it for semiconductor, for CMP, or can we use it for something else? So it gets them thinking about recycling water. And there's some additional resources here also. The script and then ultra pure water. And this is a YouTube video about the importance of ultra pure water in semiconductor manufacturing. Go back to this. So then the students will take that information, go back into the whiteboards, kind of continue their problem solving cycle, until they come up with their own solution. And then at the end of the day, when they're ready, or when the instructor's ready, the students will present their solution to the class, and then we present the organization solution. And this is another password protected section. And this is PS 0213.
That PD 2139.
Okay. So this is how MIT approached this problem. So again, it's not the only solution. It's just one solution. There's lots more out there that we're hoping that students will brainstorm and come up with.
What do we currently do with our wastewater from the CMP process?
We filter it to remove slurry particles. Then it goes through acid neutralization. 3 tanks progressively tune the pH towards neutral. Then it goes into Cambridge wastewater system. We don't even return it to gray water standards.
Could we do that? And if we did, could we use it for anything? Or maybe clean it further to make it into DI water?
Those are very good questions.
Anu, I'm very sorry if I make you sound slow. My son is a way better actor than I am.
No, this is perfect. This is perfect. I'm learning a lot.
So in the solution resources, again, the script, these are some notes for, I'm going to open these, Judy, or you want to just kind of...
What do we got here? I can't, it's too small to see. You can't make that bigger.
We have students.
Oh, wait a minute. No, hang on. Let me close this. Yeah, student solution notes. Yes, you can open that.
Okay, can you guys see that? It's a PDF file.
I can see it.
Okay, good.
Yeah, we can see it.
Yeah. Sometimes when I do this on Zoom with my own classes, sometimes they can see it, sometimes they can't. So I just have to ask every time. So anyways, this is just a quick solution description for students that is kind of short and sweet. that basically says, what fresh ideas do you have for operating a small research fab, that's more environmentally friendly. Kind of describes in brief MIT's solution. But if we go back
It says
to,
it's not ideal. What could you do
yeah,
better?
it says it's not ideal, right? So there's some other materials like how does Cambridge treat wastewater? Scarcity drives fabs to wastewater recycle. There's a great article at IEEE Spectrum in 22. Why chip manufacturers choose Arizona's desert. You wouldn't think, making semiconductors in the desert where there's no water would be a good
But
idea.
it is about recycling water. It's a great article. Yeah.
Yeah. So, but it's okay, exactly. Yeah. So, one of the things that we wanted to go back to is the teacher resources. So, let's see if I go back
There should be a home button.
yeah,
on
I'm
the
looking
bottom.
for it. I don't see it, but I can just.
Oh,
go
you're
back.
in resources. Go back to
Oh, right.
one
Okay,
of the
so I can go back to the introduction and
Yeah, I should
yeah,
put it in every slide. I haven't.
there we
Okay,
go.
there you
Okay, so for the teachers, this is where a lot of the work comes in. The password is TR Fena. What does TR stand for? I forget.
Teacher
Teacher
resources.
resource is Fena Haynes from New England Board, right? Okay. So one of the biggest challenges about teaching challenges is assessing technical knowledge, and understanding. How do you grade somebody in a problems-based learning environment? So we provide all of these resources for the teachers. The first one is the technical background. And the technical background is essentially a tutorial with all the details that a teacher would need. What do you need to know to teach this stuff? So it talks about CMP and chip manufacturing. This is the actual photo from the lab at MIT.
It's not showing, Nick.
It's not showing?
No.
Oh, okay. Hold on. One moment, please. Let's see. Maybe I have to stop share. Oh, share this tab instead. Okay. Yeah.
Oh,
You
okay.
see it now?
Yes.
Okay. All right. So again, teacher's guide. What do you need to know to teach this? All of the information that's presented in the challenge is explained in detail here. So the teacher would be able to, read this and go through it and really understand the nature of the problem. And then if we go back, share this tab instead. You guys can see we're back at the teacher resources. Yes? No?
Yes. Yep.
Okay. So the hardest part about teaching this stuff is really assessing. How do you assess student learning? So this actually came from years of research that was done by MIT, Harvard, Northwestern, Vanderbilt, University of Texas, in Northwestern back years ago when they first started getting really involved in problem-based learning for the biomedical engineering field down in Vanderbilt. And they came up with a composite method of grading students in a problem-based environment. One of them was content knowledge, because you need to have a retrievable knowledge base in order to solve problems. So in the content knowledge, you want me to click on these, or you just want me to talk about it?
Yeah, go ahead and
Okay.
Well, just a time check. There's
Oh,
Yeah,
okay.
that's what I was
All right.
concerned.
Well, yeah, they're just questions. Go to the next one because that's way more
Okay.
exciting.
So the content knowledge is basically a series of multiple choice questions that are increasing in complexity. So I'll leave it with that. And there's solutions incorporated into that. Concept knowledge was developed at in the, I think it was either physics or biology program at Cornell University years back, but really to help bring to the surface students' understanding of the relationship between concepts. And this actually, when Judy and I started doing this, we thought that, oh my God, students are going to hate this. And turns out this is their favorite part. Every challenge we've done, this is like their favorite part. So they get up on a whiteboard. We give them a bunch of concepts that were presented in the challenge. This is after they've done the challenge. And we ask them to put together a concept map. So what the goal is to take each one of these concepts and use a bubble to list those concepts and then make the connections between each one of those concepts. And the key here is if you take two individual concepts, you need to be able to connect them with a declarative statement or some words that create a declarative statement. So, for example, chemical mechanical planarization uses large quantities of water.
We can't see it, Nick.
Oh, you still? Oh, sorry.
There.
You got to speak up.
Beautiful, beautiful. It's lovely.
There you go.
It's like a spider web.
So here's all the concepts we give them. Okay, here's the concept map that we came up with. Chemical mechanical planarization uses large quantities of water. Water can be ultra pure. Water can be gray water. If it's not, it's potable water. It's wastewater. Wastewater, let's see. If we continue, gray water can be sent to public sewers. Public sewers needed for sending is needed before sending to neutralization. So every one of these concepts that we cover in this challenge should generate a declarative statement. And you can actually grade students on the number and the quality of the declarative statements that they create. And we put together a scoring rubric for that. So concept validity, proposition validity, and the presentation of their concept map, because some students are very sloppy when they do this. So this is one method of assessing student knowledge. So the hardest part of this was, how do you assess problem solving ability? So problem solving ability, and okay, you guys can
That
see
worked.
it.
Yep.
Yeah.
Yep.
Okay. So this was a slight departure from what Vanderbilt University did, in that they defined problem solving ability as the ability to transfer new information gained to new and novel situations. Which is a good way, but then it just makes it more difficult to teach, because then you have to come up with a similar problem where they have to take that knowledge and reapply it. So what we thought was, well, problem solving ability is all about process. So it's a formative evaluation. So what we ask students to do is go back to the whiteboards and then clearly explain in words, what their thought process was at every phase. So the problem analysis, the independent research, brainstorming, testing the idea, and then explain their solution as compared to the organization's solution. So it's we originally called this a reflective journal, but technical students don't like anything that sounds soft and squishy like that. So we called it final challenge report or final technical report. So, but it really forces them to go back and reflect on the process that they used and what maybe would they have done differently, now that they know how somebody else did it or how their classmates did it. So I thought this was really important. And there's also a scoring rubric here as well, that allows you to grade each student or each student team on each one of those different elements, the 5 different elements. So let's see if I go back. Finally, and this is the one that we added on our own. Yeah, you guys see this again?
That worked out really well.
Okay, teamwork. And we got 2 minutes left. Here we go. So teamwork assessment was something that was added on later. We found a validated instrument for doing peer evaluation. So this is basically, if you're part of a 3, 4, 5 member team, you rate the performance of each one of your teammates.
Nick, can't see it.
Oh, you can't see. Oh, sorry.
There you go. Thanks.
Okay. Yeah, I kind of like the way this does it. You can switch the tabs on top. So you rate each one of your team members on 6 different categories or performance, and then rate yourself. And we find it interesting that whenever I do this, the person given the review is usually hardest on themselves. And if there's additional comments, circumstances, they can add that too. But these are usually emailed individually to the instructor so that it's confidential, so you don't create a rift between you and your classmates. But this is actually part of the grade. So if I go back to, let's see, this here tab, it's up to the instructor to weight each one of these different, or if they choose to use only 2, that's fine too. But basically, it's a composite score for the final grade on the project. And we find that teachers will in our experience, will use the content knowledge. A lot of them will use the conceptual knowledge and the problem-solving ability. Some people use the teamwork, some people don't. I like to use all four personally in my classes, but that's just me. But
so how can others use it? I see that we have a minute more, so maybe we can leave it
yes,
for questions, Nick.
sure.